Okay, sorry. Sometimes my camera cuts out on me before it should. I'm going to try and get through the rest of this page before that happens again, and then we'll finish up on the back. So, we're just about to start talking about how to answer these kind of conceptual questions. The first group are asking about when is this object actually in free fall. Remember, free fall is when an object is only under the influence of gravity, nothing else. Before it's launched. Well, before it's launched, it's on the ground. So it's in contact with the ground, and the thing still has to launch it. That's not free fall. Okay, that is not free fall. Gravity is not the only thing acting on it. Not the only influence on it. At the very least, the ground is influencing it. What about as it's going up? Now it's off of the ground. It's out of contact with whatever's launching it. Is gravity the only thing influencing the motion of the object at that point? Yes, it is. So that would be a yes. What about at the top of its flight? Okay, it's stopped, but yeah, gravity is still influencing it. That is another yes. Okay, gravity is the only thing influencing the motion of that ball. Gravity is about to bring that object, I keep saying ball, it's an object, or ball, whatever you want to call it, that object back down. What about on its way back down? Also a yes, gravity is the only influence. But after it's landed, no, the ground has influenced the motion. It stopped it from falling. Okay, it stopped it from moving down. The ground has therefore influenced it. That would be a no. It is no longer in free fall at that point. Describe what happens to the acceleration. Okay, we know that in free fall the acceleration is constant. As you can see, each one of these acceleration vectors is the same magnitude and points in the same direction. So all we have to say is it is constant. What about the velocity? This is a little trickier. Notice the velocity starts off pretty big, pointed upward. It gets smaller and gets smaller until at the peak there's no velocity. And then it gets bigger and bigger, but it's pointing in the opposite direction now. Okay? The velocity is showing you how the direction and the magnitude of where the ball is traveling at different points in time. So the way I'm going to describe it is that the velocity decreases to 0 at the top, then increases in the opposite direction on the way down. The velocity decreases to 0 at the top, but it increases in the opposite direction on the way down. The next question, what is the velocity at the highest point in the object's motion? We talked about this. At the very highest point, the object is neither moving up nor down temporarily. It is motionless. That means it has a velocity of 0 meters per second. This next question is a little tricky. It says, what do you notice about the velocities just after the object is launched and just before it lands? So take a look here at the size of these arrows. We know they're in opposite directions. The size is actually, and it's supposed to be, the same. It's kind of a neat little trick that if you have something in free fall, okay, or something that gets launched in free fall, goes up and comes back down, the object is going to pass the height, each height away from the ground twice, once on the way up, once on the way down. It is true that the magnitude of the velocity at each of those points will be the same, given by the same length of these arrows. However, the velocity will be in opposite directions. This velocity is up, this velocity is down. So, what we're going to say here is that these velocities, they are equal in magnitude, but opposite in direction. And we can prove this. I know I'm just saying stuff at a board right now, but we can prove this, and we will prove this when we get the motion sensor hooked up and we have a little bit more time. Third to last question, does the velocity of the object change at a constant rate? The answer to this is yes. The velocity does change at a constant rate. It's very tough to see from this drawing, or this little sketch that we've made, that the velocity is changing at a constant rate. But I want to remind you of this. I want to see if this makes sense to you. With the velocity changing at a constant rate, well, let's see, change in velocity is acceleration. And we know in free fall our acceleration is constant. In this case, a constant 9.81 meters per second squared. So if the acceleration is constant, one way to think of the acceleration is that the acceleration tells us how much the velocity changes each second. For instance, if you accelerate at 5 meters per second squared, another way of saying it is 5 meters per second. Your velocity increases by 5 meters per second for every second that you have that acceleration. So if you start from rest, you can start from rest, and after 1 second, your velocity will be 5 meters per second, a change of 5. After another second, your velocity will be 10 meters per second, another change of 5, and so on and so forth. After 3 seconds, 15 meters per second. After 4 seconds, 20 meters per second. The acceleration tells you how much the velocity changes by each second. If we assume correctly that these points are the same amount of time between them, then we would get that the object is changing its velocity at a constant rate. So the answer to that question is yes. The answer to this question, does the object's distance from the ground change at a constant rate? You can kind of tell just by looking, is no. If this is the same amount of time between here and here, and here and here, this very clearly is not traveling the same amount of distance every second. That's because it's moving faster down in these lower ranges. It's moving slower up in these higher ranges. When something's moving slower, it just doesn't cover as much distance. So this is a no. Our last question on the front concerns how much time it takes the ball to go from here to here and from here to here. You should be able to convince yourself, if you toss something up and catch it at the same spot, you should be able to convince yourself that it takes an equal amount of time for an object to go up to its peak as it does for the object to come back down. And that's a general fact that we're going to take advantage of. So, how do these times compare? The time for it to go up and the time for it to come down? They are equal. Okay? That's a very quick conceptual rundown of how free fall works when you're launching something up and having it come back down. Our next video, we're going to sum everything up, and then we're going to see some examples.